All right, so I'm going to go over a linearization problem I wrote up and kind of talk about how to linearize. So a student is exploring friction through the use of a block, plank, and rough surface. He takes a smooth plank and places the block on top, tilting the plank above the horizontal, and the block slides down the plank, meets the rough surface at the bottom, and then slides a certain distance on the surface before coming to a stop. So, it's pretty simple. It's just a block sliding down, and then it'll meet a rough surface and then come to a stop and slide a distance d. The student wants to determine the coefficient of friction, mu, between the block and the rough surface. He does this by tilting the plank at an angle theta above the horizontal and recording the distance d that the block slides across the surface. So we're going to kind of talk about that part in a second, but real quick, it's my first time doing something like this, so this is kind of cool, like having to adjust the camera and stuff. But first, we're gonna draw a free body diagram for the block while sliding down the plank and across the rough surface. So for the plank, and this is like a plank, right? It's like a flat piece of wood that he's lifting up. It's not a ramp, but it doesn't really make a difference. It's still an inclined problem incline ramp thing where you have your FG pointing straight down, and then you're gonna have the force normal kind of, at that angle, right? Perpendicular to whatever surface you're going across. Now, on the AP exam, you're not supposed to draw components, but, ideally, your Fn will equal FGY, right? If you tilt your axis like so, if this is X and this is Y, wait, give me 1 second. All right, that was just me talking to my parents, but Fn is going to equal Fgy, right? And then there's going to be Fgx. And then across the surface, it's pretty simple. There's going to be the Fg of the weight of the block. It's going to be balanced out by the normal force, and there's going to be friction, which is the reason why it comes to a stop, right? Because the velocity is to the right. So now let's go on to the next part, and maybe adjust the camera like so, and also there we go. I'll get better at this, but we're going to derive an equation for D in terms, let me read the part. Suppose the block has a mass m and is placed a distance delta x along the plank for each trial. Derive an equation for D in terms of mu, theta, m, delta x, and physical constants. So delta x, if I draw this out, if I draw our little scenario, nice, out, delta x just represents this right here, the distance along the plank. So we want to find D, right? This distance right here. And so, we want to think about what variables do we have, what variables do we not. And this is a kinematics problem. You can do this with energy if you've moved if you're at that point in your, class, but this is kinematics and dynamics, that's our unit. So, we're going to say, okay, well, for the scenario here, right, we don't know time. We can figure out acceleration using our FBD. So we'll get to that point, but acceleration, distance are the two variables we're working with. We don't know time, but what we do know is that, we can also figure out the initial speed at this point that it gets, by the bottom of the thing. So we can use this equation. V squared is going to equal V initial squared plus 2 times the acceleration times the sliding distance d, right? And we know that the final speed of the block is going to be equal to 0. So we just need to really know what the initial speed is, and we can calculate that, right? So I can even do a little side. So we'll save this equation. We'll save, okay, V initial, so we'll call this V1, right? So V1, right? How do we find V1? Well, in this case, we don't know time, but we know the distance, and we can figure out the acceleration. So we're going to use the same formula. V1 squared is going to equal V initial squared, which in this case is 0, right? Because it starts at rest, plus 2 times acceleration times change in x. Change in x being how far along the ramp it starts. So to find acceleration, we just have to use F net. So I can even do it over here. So I can say, hey, F net in the x direction is going to equal m times a times x, which is going to equal, mg sine theta, right? Because this is really FGX or MGX, and we know the x component, if this angle is theta, the x component is given by FG sine theta. So if I get rid of the acceleration, I really get if I cancel out the m, I get v1 squared is going to equal 2, and the acceleration is going to be g sine theta. So 2g sine theta change in x. What I can do is I can go back to the first equation, right? And this is v1 squared. So I get 0 is going to equal 2g sine theta change in x plus 2. Now, the acceleration in this case, we would do our F net equation again. So we would say, hey, F net is going to equal ma. This is really the force friction. And this is really Fn times mu, right? So Fn times mu, which ma is going to equal mg times mu, because, Fn is equal to Fg. I forgot to draw the tick marks. But acceleration is going to equal g times mu. So I get 2g times mu, and then for the acceleration, and then times, getting out of the screen, but times d. Now the acceleration is negative because it's pointed opposite in the direction of motion, right? And opposite in the direction of the v initial. So I just, arrange, I just add both to both sides. 2g mu is going to equal, or 2g mu d is going to equal 2g sine theta times delta x, and you notice, hey, the 2g's cancel out, and I'm gonna get, let me just slide the paper over, I'm gonna get d is gonna equal sine theta over mu times change in x. So yeah, let's flip over to the next part of this. So just like so, oh my gosh, there we go. This is good. So for each trial, the student releases the block 50 centimeters along the ramp and uses a 200-gram block. This really should be plank, not ramp, my fault. The student records values of theta and the resulting distance d that the block slides on the rough surface. The data is shown in the table below. This is our data. So state two quantities that can be used to yield a straight line. This is where the linearization part comes in, right? Because our formula, I'm gonna write it here. So we've derived that d is gonna equal sine theta over mu times change in x, right? And we need to figure out how can we make a linear relationship between theta and d. And you can see, right, if you say d is your y variable, what you can do is you can set sine theta as your x variable. So if you think about the form y equals mx plus b, you essentially get d is going to equal x, which is sine theta, and then you're going to have this change in x over mu, right? D is proportional to sine theta. So that's what you need to do. The easiest example, in linearizing, they can either give you the formula, right? Maybe you're really lucky and they say, hey, a student figures out this is the formula, right? They can give you that formula. And then it's pretty simple. You just have to find what is your proportionality. In other cases, you might have to choose an equation off the equation sheet, right? It might be a simple v squared equals v initial squared plus 2ad. Or the hardest case is where you have to derive the formula. And in this case, we derived, but what we know is that when we graph d and sine theta, we not only get a linear graph, the slope is going to be delta x times mu. So we can graph over here, we can graph d versus sine theta, and then calculate and record any necessary data points in the empty columns of the table. So I'm just going to pull out my calculator here, right? I'm going to pull this out, and I'm going to do just that. I'm going to turn all these thetas into sine theta. So sine, let me just check on degrees. Yep. So sine 15 is 0.258. So whoopsies, didn't mean to do that. 0.258, right? So, and then sine 30 is 1/2, so I can write 0.5. Sine 45, I think, is 0.707, so 0.71. And then sine 60 is 0.87 or 0.86. So now all we got to do is plot the data, and then we're going to make a sketch of the line. So, let me just, oh my gosh, there's a lot of stuff. But it's pretty simple, right? So in this case, let's actually move this up here. So I'm graphing, my independent is really sine theta, right? That's my independent variable. So I put that on my x-axis, and it doesn't have any units. But I know d is going to have a units of meters, right? Independent variable is what I'm changing. That's sine theta. The dependent, which I don't think you can see, but it's going to be d, right? So we're going to plot our data now. First, we got to pick a scale. So a good scale in this case, you could pick 0.15, right? So 0.15 along the x-axis. Really, you want a scale that's going to have all your data enclosed, right? So I know my sine theta only goes up to 0.87, so that's the scale I use. And then I'm gonna go, my d goes all the way to 1.24 meters as provided. So I'm gonna pick my scale to be something like 0.25, right? So I get pretty perfectly to 1.25. All right. Now I just got to plot the points, right? So 0.258, each tick mark here is going to be about 0.3. So 258, so this, I think would be, it's a little hard. You can use your calculator if you like. I think 0.15 divided by 3 should be 0.03. It's 0.05. Wow. Oh, sorry. Wait, 0.15 divided by 0.0 divided by 5 is going to be 0.03. Yep. So this would be 0.27, this would be 0.24, so it's going to be somewhere kind of close to here, and then I get 0.36, so, and then 0.25 divided by 5, I'm going to get 0.05. So 0.36, so I think right around here, right, so this would be 0.3, 0.5, so right around here. All right, and then the next point is 0.5. So this is 0.48, 0.5 is probably going to be around here, and then it's going to 0.72. So it's going to be kind of over here, right? And then, and this is, I just got, because this is 0.7, this is 0.75. 0.71, so that's going to be kind of around here, and that's going to be a perfectly 1. And this is nice, right? I'm already seeing this sort of linearity. And then 0.87 is going to be right here. So I'm going to graph it to 1.24, which is like right underneath, like so. Perfect. So you can see all my points form a line, which is awesome. That means I did it right. So I'm gonna now take a straight edge. I don't really have a good one on deck, so I'm gonna use this book, great book, Things They Carried by Tim O'Brien, and I'm gonna use it to make a line of best fit. Now this is not really a good thing to use, but you know what? It works for this case. So I'm just gonna draw a trend line. I'm gonna include 0.0, so I think this would be a good trend line to draw. So that was not a good trend line. I mean, it's not the worst trend line, at least the points are somewhat close. But if you had a ruler, it's gonna be way easier. It's just with a book, you can't really see, I guess. So no worries there. But we're gonna use a trend line to now determine mu. I need to pick points on my graph, right? On the line. I don't use, even though I drew it completely skewed, I pick points from the trend line, not the actual data points. So I'm gonna pick this point right here and this point right here, because they're pretty easy to figure out. So I know that the slope is going to equal change in x over mu. And to figure out my slope, I'm just going to do the 2 points I circled. So I'm going to do 0.55 minus, right, I'm just doing rise over run. So minus, I think that's 0.3. over, so 0.33, 0.36, 0.39, so 0.39 minus, and these are meters, this is in meters, minus 0.53, 0.156. I really hope I did the mental math right. And this is really just going to be 0.5 meters, right? It was given that it's placed 50 centimeters along each trial. So I'm just going to calculate the slope really quickly. So 0.55 minus 0.3 divided by 0.39 minus 0.156. So I get 1.06. Which based off that, I definitely did it wrong. 1068 is going to equal 0.5 over mu. I can rearrange, and I get that mu is going to equal, so if I do 0.5 divided by second answer, I get that mu is going to be 0.468. The actual correct answer was 0.35, so I'm pretty off, but hopefully, you can test this, right? You can say, hey, I know this is my equation, so if I were to do, I know this is the equation it's supposed to be, assuming I did it right. So if I had 0.5 divided by my answer, and then multiply it by, let's say, sine 15. It should be 0.27 meters. It is actually 0.36 meters. So I know, my line's probably wrong. But hopefully the process here has helped you figure out a little bit more about how to linearize properly. So yeah, thank you for watching.